Alrighty, this video is about rate laws and how you can determine what a rate law would be. So we're going to start with this data here, and I'll show you what happens. Okay, so the data that you saw just there is on the left-hand side, and what we're going to do is look at concentrations and how it affects the rate. Rate laws tell us how rates are affected when you change things. Now, normally we would think that if you change the concentration, it's going to change the rate of the reaction, but that's not true every single time. Like you might think if you double the concentration, you'll double the rate, but that's not true every time either. So we use rate laws to really determine what happens if we change the concentration. Okay, so here's how I'm going to do it. I'm going to look right here. Do you see how these right here are doubled? If you start at the top one to the bottom one, we multiplied by 2. The concentration is multiplied by 2. But NO2 is stayed the same. And then we're going to look over at rate. The rate has gone from 5.4 to 10^7 to 10.8. That's double the rate. So we can see that according to NH4, NH4 is really proportional to the rate. In other words, actually I should say the rate is proportional to the amount of NH4. If we look in a different way here, let's take a look at something a little bit different, like this right here has doubled. We times by 2 the concentration. This right here has stayed the same. So now if we look over at the rate is double of that. So I can see that if you double the concentration of your NO2, the rate is proportional to the concentration of NO2. So what I'm really saying if I put the two together is that the rate is proportional to NH4 positive and to NO2 minus. They're proportional to the rate. And proportional by using a constant k. It actually should be more of a little lowercase k. This right here is the rate law for this reaction. The rate law tells us what happens if you change the concentration in something. This right here is called a first order. It's on first order. Notice there's like an imaginary 1 right here. First order rate. First order reaction for NH4. This is a first order for NO2 minus, because there's an imaginary 1 here. But the overall rate law is a second order rate law. 1 plus 1 makes 2. Okay. So now I'm going to go back to here. So we just saw that this is the rate law. And the rate law is going to allow us to calculate, like, what would the rate be if I change the concentration? Now, it's you multiply by 2 the concentration, it doubled the rate. That's a first order. This one is a total of a second order because this is a first order and a first order, and it adds up to be a second order. But not all of them will be like that. Okay, like look at this one right here. Here's my reaction, and then my rate law is right here. What are the reaction orders in the rate law? According to the NO, it is a second order rate law. According to the H2, it is a first order rate law. There's a 1 there. And the overall rate law would be the 2 plus the 1 makes a 3. It's a third order rate law. So does doubling the concentration of NO has the same effect on doubling the concentration of H2? No, it does not. If you take NO into effect, if you put a 2 here, because you just doubled the concentration, if you go 2, like let's say the normal concentration would be X amount, and then suddenly you're going to put 2X amount, 2X to the second makes 4X. If you double the concentration, it will actually quadruple the rate of the reaction. While on the other hand, if you have H2, a normal rate reaction would be X amount of H2. If you double that and put in 2X to the first, which will be just twice as big. The rate would be twice or doubled. So doubling the concentration of NO, well, 2 to the second, 4, quadruple the rate, while just doubling the concentration of H2 will only double the rate of the reaction. So rate laws can tell us, if you change your concentration, how much effect will you have on the rate of the reaction. Taking a look at this equation, you can see the rate law is right here, All of the A's are the red spheres and all of the B's are the purple ones. So we're trying to find which one would be the fastest. Taking a look at the rate law, I can see that any change in concentration of B will square that value in order to create a really fast rate. While any concentration in A won't square, it'll just do it to the first power, so it's not as great of effect on the rate. So if I want to find the one that's going to have the greatest increase in the rate of the reaction, I want to find the one that has the most number of B, or purples. That would be number 3 here. Number 3 has a lot of purples in it, which means Then if I have a lot of purples, like 1, 2, 3, 4, 5, 6, 7 purples, 7 squared, that's 49. That's a big number. While right here, there's only 3 purples. 3 squared, 3 times 3 is only 9. 49 versus 9. This number 3 will be a very fast rate of reaction compared to number 2, which will actually be the slowest because it has the lowest number of B. Okay. There's some fancy math you can do here, and they explained it math in the textbook if you want to go back and read that part too. They actually counted the numbers. Like in this number 3, there's 7 purple and 3 red. Oh, if that thing will go away. You can see that there's 7 purple and 3 red in this one. The box 1 is 5 purple and 5 red, so they actually put the 5s in for the A and the B. You can calculate what the rate would be. We can see that the third one is the fastest, and the first one is the middle, and my middle one is the slowest. Okay. Now, the thing about rate law is you can only get it from data. Like if you look at this equation on the top, you can see that there's 2 N2O5. So you would think that maybe it would be an N2O5 squared, a second order. But it's not. This is the actual rate law. Or even more confusing, the bottom one. If you look at it, Cl2 to the 1/2, you wouldn't have ever expected that by looking at the equation. So you can only get this kind of stuff through the rate law by getting data. Okay, so let's go back to here. We're going to solve for K, actually. This brings me back to the screen. Okay, so this is my rate law right here. And what I want to do is actually solve for K. And I can pick any lane that I want. I could take lane 1, 2, 3, 4, 5, any lane that I want. I'm going to look at and remember which lane I actually took here. Okay, I'm going to take lane 2. And I'm going to plug and chug in the numbers. So I'm trying to find, if I know the rate, tells me the rate right here, is 10.8 times 10 to the negative 7. That equals K, that's what I want to solve for, K, the rate constant, times the concentration of NH4, boop, 0.02, times the concentration of NO2, boop, 0.2. And if I plug and chug all these numbers, I'll get a K value of 2.7 times 10 to the negative 4. That K value will be the same no matter what. If I want to take lane 6, it'll still have a K value of 2.7, 10 to the negative 4. If I want to take lane 4 and plug and chug in those numbers, it'll still be 2.7, 10 to the negative 4 every time. Now I want to take a second to think about the units. The units on this number is molarity. The units on this number is molarity. The units on this number is molarity per second. If you didn't know that, you can always check back at the table here. So if I want to find the units of K, it's going to be different for every single reaction, so I really do need to think it through. So when I solve this, like algebraically to find for K, I divided this side by M on both sides. And there's cancel, and I divided this side by this M. So I'm left with, over here, not canceling that second M, I'm left with these two on the bottom. So my K could be units of 1 over molarity times second, or you could solve it molarity to -1, second to the -1. Inverse molarity, inverse seconds. Okay, so that would be my K value. Moving right along. Okay, we're going to take a second and actually do all of these things with this data. Try to sneak it over here. Okay, I'm going to find the rate law for this. So that's when you want to look. This is the samesies, same. And this here is doubled, times 2. And this, it doesn't double, it doesn't do anything, it stays the same. So according to the B in my rate law, or the rate, is equal to K times A to the something and B to the something. If I multiply the concentration by 2 but the rate doesn't change, here's what I think in my head. I say to myself, 2 to the what equals 1, or the same. Do you see how this doubled, but this stayed the same? I'll call that 1. 2 to the 0. 2 to the 0 equals 1. 2 to the anything to the 0 power equals 1. This rate order for B is 0. 0. Let's look at the next guy. Okay, so now we got A going from 1 to 2. That's multiplying by 2. Oh, but over here, that doesn't work because that's also changed concentration. So I can't look at that. I'm going to look at a different one. I'm going to look at this from 1 to 2. 1 to 2. It multiplied by 2. And here it went from 1 to 1. That's the same Z. So then I'm going to look at my rate. 4 to 16. That definitely is different. It's multiplied by 4. So now I take a second here. And I think 2, because I doubled the concentration, to the what equals 4. Well, 2 to the 2 equals 4. That's why this is a 2 up here for a coefficient. not a coefficient, power, second power. So now I've completed the rate law. That is my rate law. If I wanted to solve for the rate constant, that's going to be my B part down here, I'm going to plug and chug in numbers. Like I'm going to take everything in lane 1. My rate is 4 times 10 to the negative 5 equals K times A 0.1 squared times B 0.1 to the 0, which was really just 1, so it doesn't matter. If I rearrange things, I'm looking at K is equal to, get out my work here, 0.0040. 0.0040. 2 sig figs that I want, because this is really 4.0, so I wanted 2 sig figs in my answer. If I look at all these numbers here, this has 2 sig figs, that's the lowest, so I'm going to take that. Checking out my units. This one canceled, I don't really have to worry about it because it's to the 0 power, so it doesn't really exist. If you look at this though, this is molarity squared, and this is molarity per second. So if I divide both sides by molarity squared, then I can see I'm going to get, take that out, cancel that out. Once again, I'm getting molarity to the negative 1, seconds to the negative 1. Okay, and the last part of my problem here, part C, man, I'm losing space here. Part C is where I want to take this rate law, whoop, right here, and I'm just going to plug and chug in these numbers. So I'm really going to find the rate when I know K, which is 0.0040, I just solved for that, times the concentration of A, in this case they're telling me it's 0.05, times the concentration, oh, that's squared. That's what this blue 2 is for. Times the concentration of B to the 0 power, well really it doesn't matter because that's going to turn into 1. So actually you can find the rate for here is 1.0 times 10 to the negative 5, and rate having molarity per second for units. Okay, there I'm done with that problem. I'm getting short on time, so I'm going to have to talk faster, just to warn you. Sorry. Okay. So, I got some practice problems for you to try in class here, and I'll help you out if you need help with that, but it's the same kind of idea, looking at data just like we did and solving these type of questions. But now I want to show you like these graphs. One way to get data is by graph, and one way to get data is in the data tables part. So how can we do if it's a graph? It's actually easier. This top part here is different graphs from data, and this bottom part is a copy and paste of the AP equation sheet, the ones that we care about. So I'm going to show you what we got here. I'm going to kind of breeze through things and then recap at the end. Okay, so if you take this is the first order rate law in red, first order rate law. If you use fancy calculus and you integrate things and blah, 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 doing fancy calculus, you find this middle equation is the integral of it. And if you rearrange the equation, you do some fancy math, you get this one down here. Whoop, whoop, whoop. And the way it's arranged, it's a y equals mx plus b situation. So I can actually graph it. ln is my y equals mx plus b. Okay, so you can see sometimes I have a straight line, sometimes it's curved. Second order, I can do that same thing and integrate things. I have again y equals mx plus b. I can graph that, that's this one on the right. Notice I have a different y value here. Now it's a 1 over a. Before it was the natural log of a. If we go to 0 order, notice what we're doing. We've got a concentration of a versus time. So every time that I did some sort of graph, the only way I got a linear line is if I graphed it the right way. That was kind of a terrible sentence, so let's take a look at it. In conclusion, this right here, when you integrate things, this would be for a first order reaction. That's an important thing to write down. This one right here is used for a second order reaction. That's important to write down. And this thing that you can't really see very well is for half-life sort of stuff, so I'm going to come back to that later. But really first order, second order, and then that third type of graph is for a 0 order. So let's take a look. This first order, ln. This graph here is first order. See how it has ln in it? ln in it, first order. This one here is your second order equation. See it has 1 over a in it? That's this one, 1 over a in it. So first order, second order, and the other one, a over t, is our 0 order. So now we want to ask ourselves, I got all this data, how do I know what order reaction I have here? You have to find the one that's a linear. Do you see how this one is linear and it's the only one that's linear? The only reason it's linear is because it is following the order that is used for this graph. This is ln of something, this is ln of something. If something is ln of a graph, which this is, and it's linear, it's a first order reaction. That's what I got here. Let me show it to you in the next one. I might run out of time. This is an AP question. My first part is find the order of the reaction. So I look at these graphs and I try to find the most linear one. That one is not linear. This one down here, but this one is a better linear one. This one is a linear reaction. Okay, now I look over here on the y. I see it's a 1 over something sort of thing.